myself, B.Hemalatha, working as an assistant professor in Department of Electronics and Communication Engineering, Bharat Institute of Higher Education and Research. In this video, we are going to discuss about the topic frequency response analysis and design. Let's see some definitions related to frequency response. First, we are going to see about the definition of frequency response, and next we'll move on to methods of conventional control system. Third one is need for frequency response. Fourth one is frequency domain specification, and next one is implementation of frequency response systems. And then we'll be moving on to introduction to Bode plot. In that, we will be discussing about transfer function, poles and zeros, mechanism in solving Bode plot. And then the next part will be a stability analysis. In that, we'll be discussing about minimum phase transfer function, non-minimum transfer function, gain margin and phase margin, gain crossover frequency and phase crossover frequency. This is the outline of this session. Let's begin with frequency response. The steady state response of a system for an input sinusoidal signal is known as the frequency response. Okay, if you are going to apply a sinusoidal signal as an input to linear time invariant system, then it produces a steady state output, which will also be a sinusoidal signal. The input and the output sinusoidal signal have same frequency but with different amplitude and phase angles. Okay, for analyzing this frequency response, there are few methods. That is, first method is analysis method, second one is synthesis method, third one is performance method, and last one is stability in frequency domain. These are the methods of frequency response. Actually, as the name implies, frequency response analysis is being carried out in frequency domain rather than time domain. Okay, here while finding the frequency domain characteristics, we can able to obtain the time domain properties from it. Okay, so here for linear time invariant system, the Laplace transform of input and output are related to each other by a transfer function. As we all know, the definition for transfer function is the Laplace transform of output by Laplace transform of input, assuming all initial conditions are 0. Okay, so this is the Laplace domain transfer function representation. Okay, see the block diagram which I have given here. Input is been given as R of S, that is nothing but the reference input, and the output is nothing but represented as C of S. It is nothing but the controlled output. So the transfer function T of S is represented as C of S divided by R of S. That is, according to the definition, output by input. Output is C of S and input is R of S. So T of S will be equal to C of S divided by R of S. Here, in frequency response analysis, the system is excited by a sinusoidal input of fixed amplitude and varying frequency. You can see here in the given diagram, the input signal is a sinusoidal signal, that is R of T is varying with respect to T, and the amplitude is fixed and frequency is varying depending upon the time. Okay, so the input signal is represented as A sine of omega t, and the output signal, if you are seeing here, the amplitude is same, but the phase angle is different. So B into sine of omega t plus phi. Okay, this is the representation of input and output in frequency domain for a sinusoidal signal. Next, we'll move on to the representations or equations, how we are going to give it in frequency domain. So, if you are going to take a stable LTI system, if you are going to apply a sinusoidal input of amplitude R and frequency omega in time domain, then the equation can be given as R of t is equal to R into sine of omega t. Here R represents the amplitude, omega represents the frequency in time domain, and it is given in R of t. Okay, that's so time domain representation. So here the steady state output of the system will be again a sinusoidal signal of the same frequency, but probably with a different amplitude and phase. So R of t in the previous equation we have written for input. Now we are going to write the equation for output. Output is nothing but C of t, which is equal to C into sine of omega t plus phi. So to carry out the same process in frequency domain for a sinusoidal steady state analysis, we will be replacing S is equal to j omega. Okay, generally I say T of s is equal to C of s divided by R of s. From that representation, we can write the equation for C of s as T of s into R of s. So what I said, if you are going to do it, the analysis in frequency domain, s will be represented with j omega. So here, instead of s, I am representing j omega. So C of j omega is equal to T of j omega into R of j omega. This is the representation of output in frequency domain. Now, the input, output, and the transfer function have now become complex, and they can also be represented with their magnitude and phases. See, actually, whenever you are going to take the equation, there will be a magnitude and the phase angle. So, for an input, output, and the transfer function, we can able to represent the magnitude and the phase angle as given. See, for input, R of j omega is equal to magnitude of j omega, that is R of j omega magnitude. Angle of R of j omega represents the phase angle. In output, C of j omega is the actual output, which is equal to the magnitude representation is magnitude of C of j omega, and the angle representation is angle of C of j omega. In the transfer function, T of j omega is equal to magnitude of T of j omega into angle of T of j omega. So we can able to obtain both the magnitude and the phase angle for input, output, and the transfer function using this method. Okay, so let us consider the transfer function for a closed loop system. For closed loop system, the equation is, the general representation of transfer function is g of s divided by 1 plus g of s into h of s. This is the general transfer function for a closed loop system. Okay, if I want to convert this transfer function in terms of frequency domain, what is the step we have to follow? We have to get substitute s is equal to j omega. So in the previous equation, if I am substituting s is equal to j omega, we are getting g of j omega divided by 1 plus g of j omega into h of j omega. So here t of j omega is nothing but the frequency response function, FRF, or sinusoidal transfer function for the given system in frequency domain. So now, if I am going to represent the transfer function T of j omega in magnitude and in terms of angle, then the equation will be written as T of j omega is equal to magnitude of T of j omega into angle of T of j omega. Okay, so this function is very complex, right? So it can also be written in terms of real and imaginary parts. So that's what I've given in the second step. T of j omega is equal to real part of T of j omega plus j into imaginary part of T of j omega. So now we are just separating the transfer function in terms of real part and the imaginary part. Okay, so as I said, we can able to split the real part and the imaginary part. Then z is equal to a plus bj is the complex number representation for real and imaginary parts. So in that, if you are going to obtain the magnitude equation, then magnitude of z will be equal to root of a plus bj into a minus bj, which is nothing but the representation of a square minus b square within the square root. So square root of a square minus b square is the actual magnitude of the given function. And similarly, if you are going to write the phase angle, angle of z is equal to tan inverse of b by a. This is a general representation of finding the magnitude and the phase angle in frequency domain. So that the same process, if I am going to apply for closed loop function, that is closed loop transfer function, then you will be getting T of j omega is equal to g of j omega divided by magnitude of 1 plus g of j omega into h of j omega. If you are going to represent an angle, then it will be the angle of T of j omega is equal to angle of g of j omega minus angle of 1 plus g of j omega into h of j omega. This is the magnitude and phase angle representation for the transfer function. Okay, frequency response function. That is, we are substituted s is equal to j omega. So this implies the transfer function which is represented in terms of frequency response. So this can also be called as gain and the phase characteristics of the frequency response analysis. Next, we'll move on to methods of conventional control system. Okay, in conventional control system, there are two methods for predicting and adjusting the system performance. Okay, so without resorting to the solution of the system, differential equation. Without changing the system differential equation, we can able to improve the performance of the given system. That the performance can be improved by two methods. One is root locus method and other one is frequency response method. First, we'll discuss in detail about root locus method. So precise root locations are known and actual time response is easily obtained by means of an inverse Laplace transform. Okay, by taking an inverse Laplace transform and by plotting the poles and zeros, we can able to obtain the root locus response for the given transfer function. So what are the advantages of this root locus method is good indicator of transient response. See, actually we have discussed in the previous videos, we have two responses. One is transient response and the other one is steady state response. Okay, that if you are going to indicate the transient response, then root locus method will be a precise one. Okay, so second one is explicitly shows location of all closed loop poles, because we are going to mark all the poles and zeros in the S plane. So it will be easily understood. Okay, trade-offs in the design are fairly clear. What are the disadvantages of this root locus methods are? It requires a transfer function model, right? Actually, they will be giving T of S is equal to some expression will be given. That is the transfer function. So from that only we will be locating poles and zeros. And it is difficult to infer all performance metrics. Okay. So we can't able to obtain the exact value or exact response. Okay. Using this root locus method. Third one is hard to determine response to steady state. And fourth one is hard to infer stability margins. So these are the disadvantages of root locus method. So in order to overcome these drawbacks which is obtained, we are moving on to frequency response method. Here, design of feedback control system in the industry is probably accomplished using frequency response method. Okay, that is in many industries they are using frequency response method rather than root locus method. Why? Because it provides good designs in face of uncertainty in the plant model. Okay, that is one point. We can able to obtain the good performance if there is any uncertainty obtained in the plants. Okay, second point is noise signals which is present in the system will be resulting in poor performance. Okay, but if you are going to use the frequency response method for analyzing the system, we will be obtaining good performance. These are the 2 points why we are going for frequency response method. Then when the transfer function of the component is unknown, the frequency response can be determined experimentally and an approximate expression for the transfer function can be obtained from the graph of the experimental data. Okay, if you are not having the transfer function also, we can able to obtain the output. That is, we can able to increase the system performance experimentally, and from the graph which is obtained using the experimental data, we can able to analyze the system. Okay, so here, as I said earlier, the frequency response analysis are carried out in frequency domain rather than the time domain. So frequency, what are the advantages of frequency methods? That's what when related with root locus techniques I've listed here. First one is can infer performance and stability from the same plot. Okay, it can use measured data rather than the transfer function model. Okay, no need of transfer function model. We can measure data directly using the experimental analysis. Third one, design process can be independent of the system order. Time delays are handled correctly. And graphical techniques, analysis and synthesis are quite simple in case of frequency response methods. Let us see the response of frequency domain. Before going to that, we should know about the few terms. Before going for the analysis or synthesis, we should know the basic definitions which has been used in frequency domain analysis. Okay, that is called as frequency domain specifications. Okay, first one is resonant peak. It is represented as M suffix R, capital M suffix R. Okay, so maximum value of M of j omega when omega is varied from 0 to infinity. You can see here the graph. What is the resonant peak? A maximum value when omega R is varied. Okay, so this is the frequency versus a magnitude, right? So at the point where omega r reaches the maximum value is nothing but the m suffix r. That's what they have given. Maximum value of m of j omega when omega is varied from 0 to infinity. MR depends on the damping ratio zeta only and indicates the relative stability of the stable closed loop system. This resonant peak depends on the damping ratio zeta. Okay, and it provides a relative stability of the stable closed loop system. And here, if you are using a large MR, that is large resonant peak, in large overshoot of the step response, we'll be obtaining large resonant peak in large overshoot of the step response. As a rule of thumb, MR should be between 1.1 and 1.5. If this is the value, if you are going to maintain for resonant peak, then we'll be obtaining the stable output. Okay, so MR is equal to 1 divided by 2 zeta into root of 1 minus zeta square. If you are seeing the formula, the MR is depending upon the damping ratio zeta only. Depending upon the value of zeta, the MR is going to vary. That's what they have given in the second point. MR depends on the damping ratio zeta only and indicates the relative stability of the stable closed loop system. Second specification is resonant frequency omega r. Okay, the frequency at which MR occurs is nothing but the resonant frequency. See, the maximum value where you are getting the corresponding frequency is nothing but the resonant frequency omega r. Omega r is equal to omega n into root of 1 minus 2 zeta square. Here also, the omega r is nothing but the resonant frequency. Omega n is nothing but the damped natural frequency. Okay, zeta is the damping ratio. So note that omega r is different from both the undamped and the damped natural frequencies. Next, the third one is cutoff frequency. The frequency at which m of j omega has a value of 0.707 is nothing but the cutoff frequency. It is the frequency at which the magnitude is 3 decibels below its zero frequency value. Okay. Fourth specification is bandwidth. It is represented by omega suffix b. It is a range of frequencies in which magnitude of the closed loop system is 0.707 times of MR. Okay, so bandwidth W will be 0.707 times of MR, 0.707 into MR. Bandwidth is directly proportional to the omega n natural frequency and given an indication of the transient response characteristics of the control system. So now if the bandwidth is larger, then the system response will be very faster. Okay, it is also an indicator of robustness and noise filtering characteristics of a control system. Bandwidth is nothing but an indicator of robustness and noise filtering characteristics of a control system. Then next one is, we should know this terms which is useful for drawing the response using the frequency domain specifications. First, let's discuss about phase crossover frequency. Okay, the frequency at which the phase plot crosses minus 180 degrees is nothing but phase crossover frequency. Okay, so now if you are taking this thing where we are having minus 180 degree, see minus 180 degree is here where it cuts the phase plot. The corresponding value is frequency is nothing but the phase crossover frequency. The corresponding frequency is nothing but the phase crossover frequency. Gain margin is nothing but it is the increase in open loop gain in decibels required to drive the closed loop system to verge of instability. Gain margin is nothing but, see now this is a 0 dB line. Okay, where this 180 degree line cuts the phase curve, from there we are extending till the magnitude curve. Okay, so the difference between the 0 dB line and the magnitude plot, that is nothing but the gain margin. Next, moving on to gain crossover frequency. The frequency at which gain or magnitude plot crosses 0 dB line. So if you are seeing here the 0 dB line where it cuts the magnitude plot, from there we'll be extending up to phase plot. Okay, so there we are having this blue line, right? So minus 180 degree is this one. So the difference between this minus 180 degree and the where it cuts the phase plot, that region is nothing but, that value is nothing but the phase margin. Okay, and it is the increase in open loop phase shift in degree required to drive the closed loop system to the verge of instability. These are the four terms which is related in analyzing the stability of the given transfer function in frequency domain analysis. Okay. So now a variety of ways to display frequency response analysis. In that way I have listed here. First one is polar plot. It can also be called as Nyquist plot. Here real versus imaginary part of G omega in complex plane will be drawn. Okay, for that analysis we will be obtaining the response. It is but if you are going to use this type of analysis in polar plot, it is hard to visualize and not useful for synthesis, but gives definite test for stability, and it is a basis of robustness analysis. Okay, if you're going for polar plot, it is very hard to visualize, so we can't able to visualize the plot which has been drawn for the given transfer function. Second analysis is Nichols plot. Okay, here also we are going to obtain the magnitude versus angle. Okay, that is magnitude of G of J omega versus angle of G of J omega. Here, if you are going to use this type, it is very handy for system with lightly damped poles. Okay, if it is heavily damped poles, then this analysis will be very difficult, or it will be more complicated. So we are going for the third one is Bode plot. Here, logarithmic value of magnitude of G of J omega and angle of G of J omega versus log frequency is been taken as a plot. Okay, if you are taking the Bode plot, the left hand side will be representation of magnitude, right hand side will be the representation of angle, and the x-axis will be the representation of frequency. Y-axis, one side will be a magnitude representation, y-axis, right hand side will be the angle representation, and the x-axis will be the logarithmic, that is frequency representation. So this is the very simplest tool for visualization and synthesis in frequency domain. Here we will be plotting the graph in terms of decibels. If I am going to plot the graph in decibels, then this is a formula for calculating the given obtained value in terms of decibels. So 20 log of the gain value will be the formula for converting the value into decibels. So here the Bode plot of the transfer function is a useful graphical tool for the analysis and design of linear control system in frequency domain. Okay, it is a graphical tool for analyzing and designing the linear control system in frequency domain. Okay, what are the advantages of using this Bode plot? I've listed here 5 points. First one is it can be sketched approximately using straight line segments without using a computer. That is, using the scale itself, we can able to draw the magnitude value, and with free hand we can able to represent the phase angles. Okay, the phase curve. Okay, that is the first advantage of Bode plot. Second one is relative stability characteristics are easily determined. Third one is effects of adding controllers and their parameters are easily visualized. So whatever controllers we want to change, we can able to change, and we can able to see the processing which is happening inside the controllers, and rapid manual graphing is possible. And fourth, last point is wide range of amplitude ratio and frequency, both low and high are conveniently displayed. These are the 5 points which is been highlighted for obtaining the response using Bode plot in frequency domain. So sinusoidal transfer function may be represented by two separate plots, that is magnitude in decibels versus frequency, logarithmic frequency, that is one plot, and the second plot is phase angle in degrees versus frequency, that is logarithmic frequency. As I said earlier, we are going to have magnitude on the left hand side, angle on the right hand side, with the common frequency on the x-axis. So magnitude versus frequency is one plot, phase angle versus frequency represents the other plot. Let us discuss about the diagram, plots of Bode diagram. Magnitude of frequency response function in decibels is given by 20 log of G of J omega. Whatever value of G of J omega we are obtaining, if you are using this formula, we are going to obtain the value in decibels, which will be drawn on the linear scale versus frequency on the logarithmic scale. Second one is phase. Okay, phase of the frequency response function on a linear scale versus frequency on the logarithmic scale. See, you can see the response I have given here, magnitude in decibels versus frequency. So this is a representation of magnitude curve, and phased in degrees with us, which is versus frequency is representation of phase curve. So this will be drawn with the help of the scale. Magnitude will be drawn with the help of the scale, and the phase angle will be drawn with the free hands. This is the way we will be obtaining the graphical representation for the given transfer function. Okay, so transfer what is transfer function? It is defined as the ratio of Laplace transform of the output to the input with all initial conditions are equal to 0. So it can be factorized in the following form I have given here. As we all know that the numerator polynomial represents the zeros and the denominator polynomial represents the poles. So g of s is equal to k into s plus z1 into s plus z2 etc. up to s plus zn divided by s plus p1 into s plus p2 etc. into s plus pn. So this is the actual representation of the transfer function in frequency domain. So the roots of the numerator polynomials are represented for zeros and the roots of the denominator polynomial are called as poles. Okay, so how we are going to draw the poles and zeros in S plane? Okay, the transfer function can be constructed from four basic factors: gain, k, a constant, integral factor 1 by j omega, a derivative factor j omega. 1 by j omega means it is representing the zeros, okay, and j omega means it is representing the poles. Numerator polynomial is representing zeros and the denominator polynomial is representing the poles. So that is nothing but poles or zeros at the origin. Then first order factor, it can be in terms of 1 divided by s plus a, like that. Okay, so according to that, simple lag 1 divided by 1 plus j omega t, or lead in terms of 1 plus j omega t. If you are going to represent using lag compensation, then 1 divided by 1 plus j omega t. If you are going to use lead compensation, it will be represented as 1 plus j omega t. So this is a representation of real poles and zeros for the first order system. Quadratic factor will be quadratic lag or lead. According to this, second order function will be proceeding. So this is the graph I have shown here. This is the transfer function they have given. S plus 8 into S plus 14 divided by S into S plus 4 into S plus 10. So what are the poles and what are the zeros here? Numerator represents the zeros. So S is equal to minus 8, S is equal to minus 14 is representing the zeros. So zeros will be represented with the circle and the poles will be represented with the cross mark. So what is the point? Zeros we have minus 8 and minus 14. You can see here minus 8 is represented with the circle and minus 14 is represented with the circle. Similarly, poles if you are considering for S factor, S is equal to 0 and the second factor is S is equal to minus 4 and third factor S is equal to minus 10. So 0, then minus 4, then minus 10. So it is represented with a cross mark. So this is the origin and it is the axis is drawn between omega j omega axis versus real axis. That is, this is imaginary axis and the real axis. According to the given transfer function, we are going to mark the poles and zeros of the given transfer function. Let us consider about the gain factor. First, gain factor. Okay, so the gain factor multiplies the overall gain by a constant value for all frequencies. It has no effect on the phase because k is nothing but the gain factor. It is considered as a constant. Initially, we will be taking it as 1 and we will be proceeding with the analysis, and then finally we will substitute that value and find the value of k. So only it is a constant. It is related with constant. So it is related only with the magnitude, which has no effect on the phase. So g of s is equal to k. S is represented with j omega. Again, it is equal to k. Okay, so magnitude if you are finding 20 log of g of j omega, if k value is taken as 1, then we will be obtaining the magnitude value. But phase is 0. So that's what you have represented in the graph here. 20 log k, this is the actual value will be obtained when k value is substituted as 1. Okay, here there is no phase, so obviously it is in the 0 line. Now, if I am going for the integral factor 1 by j omega, that is poles at the origin. Magnitude is a straight line with a slope of minus 20 decibels. Okay, simple thing. If you are having the positive factor in the denominator, you will be representing with minus 20 decibels. If the same factor is used in numerator, then it will be represented with plus 20 decibels per decade. So here we are having the j omega factor on the denominator. That is integral. It is acting as an integral factor. If it is acting as an integral factor, then the slope will be minus 20 decibels per decade. Okay, so phase is constant at minus 90 degree at all frequencies. Okay, so this is a constant value. For magnitude, it will be minus 20 decibels per decade, and for phase, it is minus 90 degree. This is the constant, that is standard value for integral factor 1 by j omega. So g of s is equal to 1 by s, g of j omega is equal to 1 by j omega, which is equal to minus 1 by omega into j. If I am writing the magnitude equation, magnitude is equal to 20 log of g of j omega. In that place g of j omega, we got 1 by omega, right? So that's what I am taking 1 by omega. So if I am keeping on varying the values of omega, then we will be getting the decibel value of magnitude. Okay, that is equal to minus 20 log of omega. So for different values of omega, we can obtain the different magnitude values for the given frequencies. That is omega is representation of frequency. If frequency is keeping on varying, then we will be getting different values of magnitude. And phase angle is minus 90 degree. Keeping these points in mind, you can see here the decibel line is varying from 20 to minus 20. Okay, so now this line is represented for a minus 20 dB per decade slope. If you are taking your angle, it is minus 90 degree. Similarly, double pole at the origin. See, actually in the previous slide, we had only 1 by j omega. For example, if you are having 1 by s square, okay, s square means j omega square. So 2 poles, right? That is nothing but a double pole. If it is double pole in the denominator integral factor, then minus 20 will be becoming minus 40. And the angle will be minus 90, it will become minus 180. Okay, so it is an integral factor of s square term, that is second order term. G of s is equal to 1 by s square, g of j omega is equal to 1 by j omega the whole square, which is equal to minus 1 divided by omega square. Okay, from that we can able to obtain the magnitude 20 log of 1 by omega square, which is nothing but minus 40 log of omega. So for different values of omega, we will be obtaining different values of magnitude. As I said earlier, if it is a s square term, right? So minus 90 plus minus 90 will become minus 180. That is the phase angle for double pole at the origin. So now it is reduced from 40 decibels to minus 40 decibels per decade. Okay, here the angle is minus 180 degree. So now let us go to the derivative factor, that is the s term in the numerator. If s term in the numerator means it is representing the zeros, right? So now the magnitude is straight line with a slope of positive value of 20 decibels per decade. So omega is equal to 1 radians per second. Phase is constant at 90 degree at all frequency. So if it is the derivative factor, we will be having the positive magnitude and a positive phase. Okay, if it is an integral factor, we will be having the negative magnitude and the negative angle. So g of s is equal to s, g of j omega is equal to omega into j. So m is equal to 20 log of g of j omega, from that 20 log of omega. So by varying the values of omega, we can get this value. So phi is equal to 90. You can see the response here I've given. It is varying from minus 20 decibels to plus 20 decibels. This line is representation for 20 dB per decade slope, and the angle is plus 90 degree. So the same thing which has happened for derivative factor, that is double zero at the origin. For example, if you are taking s square in the numerator, then what will happen for s 20 decibels, the other s it will be 20 decibels. 20 plus 20 is 40 decibels per decade. For omega is equal to 1 radians per second, and angle is 90 plus 90 will become 180. So 40 log of omega, for different values of omega will be obtaining the magnitude, and for phi it is 180 degree. You can see the response here, it is varying from minus 40 to plus 40. This blue line is a representation of 40 decibels per decade slope, and this is nothing but the angle, which is nothing but 180 degree. Okay, this is the general concepts which we should know for drawing the Bode plot. Then we'll move on to stability analysis. Transfer functions which have no poles or zeros on the right hand side are called the complex plan, or called minimum phase transfer function. Okay, so if you are not having any poles or zeros on the right hand side of the complex plane, then that type of functions are called as minimum phase transfer function. Okay, on the other hand, if you are going to have poles or zeros on the right half of the S plane, then that type of functions are called as non-minimum phase transfer function. So the major disadvantage of Bode plot is that stability of only minimum phase systems can be determined using Bode plot. That is, non-minimum phase transfer function cannot be obtained using Bode plot. Okay, from the characteristic equation, that is the denominator polynomial, if it is equated to 0, that is nothing but a characteristic equation. So if you are considering the general closed loop transfer function, we will be having g of s divided by 1 plus g of s into h of s. So the denominator polynomial here is 1 plus g of s into h of s. That is equated to 0, or we can write it as g of s into h of s is equal to minus 1. Okay, now how will you write the magnitude and phase angle for this? Okay, 20 log of g omega into h of j omega, which is equal to 20 log 1, which is equal to 0 decibels. Similarly, angle of g of j omega into h of j omega is equal to minus 180 degree. Thus, when the magnitude and phase angle of a transfer function are 0 decibel and minus 180 degree respectively, then the system is marginally stable. Why? Because we are obtaining gain margin and phase margin based on this 0 decibel value and minus 180 degree only. So minus 180 degree angle where it cuts the phase curve, the corresponding frequency is nothing but gain crossover frequency, and the value is nothing but the gain margin. Similarly, from 0 decibels, we are obtaining the phase margin and phase crossover frequency. So this is why we are taking 0 decibel and the minus 180 degree for obtaining the specifications which is needed in Bode plot. So if the frequency for which phase becomes equal to minus 180 degree or gain is below 0 decibel, then the system is stable. Further, if the frequency for which gain becomes equal to 0, phase is above minus 180 degree, then the system is unstable otherwise. Okay, so thus the relative stability of minimum phase transfer function can be obtained according to these observations. Okay, based on these points, we can able to obtain the relative stability of the given system. Drawbacks of frequency response systems is applied only to linear system. We can't able to use Bode plot for non-linear system. Similarly, frequency response for existing system is possible to obtain if the time constant is up to few minutes. Okay, time consuming procedure because it is a tedious process, so it is time consuming and old and back dated method. Okay, so this is the oldest method. Thank you.